Have you ever washed your hands and felt like the soap just wouldn't lather up? Or maybe you've seen those annoying white, chalky spots on your glass dishes after they dry. That frustrating experience isn't because of your soap or your dishwasher. It's because of your water. And today, we're going to talk about the culprit, hard water. Hello, engineering students. Welcome to the channel. In this video, we're going to break down one of the most fundamental topics in engineering chemistry, the hardness of water. We'll start with what hardness actually is and what causes it. Then we'll cover the two main types, temporary and permanent hardness. After that, we'll learn about the different units used to measure it, and most importantly, we'll walk through a classic numerical problem, step by step, so you can solve it with confidence in your exams. By the end of this video, you'll understand hard water inside and out. Let's get started. Okay, so let's start with the official definition. Technically, it's a measure of how much soap the water uses up before it can start forming a proper lather. In simple terms, hard water is stubborn water. It resists making bubbles with soap. Think about making a sweet drink. You add sugar to water, stir it, and the sugar disappears, right? It's dissolved. Hard water is just like that, but instead of sugar, it has invisible, dissolved minerals, specifically salts of calcium and magnesium. These dissolved minerals are what make the water hard and interfere with the soap. Imagine this. When you add soap to soft water, the soap molecules are free to do their job and create lots of lather. But now let's add those calcium and magnesium ions into the water. Instead of making bubbles, the soap reacts with these minerals and forms a sticky, gooey substance called scum. That's the stuff that leaves a ring in your bathtub and makes your clothes feel stiff. This isn't just about soap. Understanding hard water is critical in engineering. In our homes, it affects how well our detergents work. But in factories and power plants, hard water can be a disaster. Over time, these minerals build up inside pipes, boilers, and cooling towers, forming a thick, hard layer called scale. This scale can clog pipes completely and cause boilers to overheat and even explode. So measuring and treating hardness is a very big deal. So we know what hardness is, but it turns out there are two different kinds. First, we have temporary hardness. This is caused by the presence of dissolved bicarbonates of calcium and magnesium. It's called temporary because you can remove it just by boiling the water. Second, we have permanent hardness. This is caused by dissolved chlorides and sulfates of calcium and magnesium. Boiling does not remove this type of hardness, which is why it's called permanent. Here's a great way to remember the difference. Temporary hardness is like dissolving sugar in cold water. If you heat that water, some sugar might come out of the solution and settle at the bottom. Boiling removes it. Permanent hardness, on the other hand, is like dissolving salt in water. You can boil that salt water all day long, but the salt isn't going anywhere. It's permanent. This table is your cheat sheet. If the salt is a bicarbonate, its hardness is temporary. If it's a chloride or a sulfate, its hardness is permanent. Simple as that. Knowing the type of hardness tells an engineer how to treat the water. If a water sample has only temporary hardness, a simple boiling process might be enough. But if it has permanent hardness, you need more advanced methods like ion exchange or reverse osmosis to soften it. Okay. So we can classify hardness, but how do we measure it? Let's talk about the units. There are 4 common units for measuring hardness. This looks complicated, but it's not. Think of it like measuring your height. You can measure it in feet, inches, or centimeters. They are different units, but they all measure the same thing. In water chemistry, we do the same. We measure hardness using different scales, but they all relate back to one standard substance, calcium carbonate, or CaCO3. We express the hardness as if it was all caused by calcium carbonate. This gives us a simple, uniform way to compare the effects of different salts. For all practical purposes in your exams, you can assume that 1 milligram per liter is exactly the same as 1 part per million. The only thing you really need to remember is the conversion rule. Memorize this. It's all you need from most unit conversion problems. You'll see these units everywhere. Water quality reports for your city, results from a chemistry lab, and specifications for industrial equipment all use these units to describe how hard the water is. Okay, that's all the theory we need. But how does this actually work in a problem? Let's dive into an example you might see on an exam. All right, grab a pen and paper. Here's our problem. The first and most important rule of hardness calculations is this: you can never just add the masses of the salts together. They have different chemical structures and molecular weights. We have to convert each of them into their calcium carbonate equivalent. It's like converting different currencies into one standard currency, like US dollars, before you add them up. The formula to do this is equivalent hardness equals the mass of the salt divided by the molar mass of the salt, all multiplied by 100. We multiply by 100 because the molar mass of our standard, CaCO3, is 100. First, we need the molar masses of our two salts. For calcium sulfate, CaSO4, calcium is 40, sulfur is 32, and oxygen is 16. So, 40 plus 32 plus 4 times 16 equals 136. For magnesium bicarbonate, MgHCO3, 2, magnesium is 24, and the bicarbonate part is 61. So, 24 plus 2 times 61 equals 146. A common mistake here is messing up the molar mass calculation. Always double-check your math. Now we just plug the values into our formula for calcium sulfate. The mass is 20.4 milligrams, and the molar mass is 136. So the hardness caused by the calcium sulfate is 15 milligrams per liter in terms of calcium carbonate. Next, we do the same thing for magnesium bicarbonate. The mass is 16.2 milligrams, and the molar mass is 146. The hardness from this salt is 11.1 milligrams per liter. Now that both salts are in the same standard unit, we can finally add them together to find the total hardness. Total hardness equals 15 milligrams per liter plus 11.1 milligrams per liter, which equals 26.1 milligrams per liter. And that's our final answer. The total hardness of the water sample is 26.1 milligrams per liter. See? Once you follow the steps, it's not so bad. All right, let's do a quick recap of the most important takeaways. 1. Hard water is caused by dissolved calcium and magnesium salts, which stop soap from working and can clog pipes. 2. Hardness can be temporary if it's caused by bicarbonates and can be boiled away, or permanent if it's caused by chlorides and sulfates. And 3. The golden rule for calculations. Always convert the mass of each salt into its calcium carbonate equivalent before you add anything together. If this video made water hardness a little less mysterious, please hit that like button. Let me know in the comments what topic you're struggling with, and I'll try to cover it next. And of course, don't forget to subscribe for more simplified engineering videos. Thanks for watching, and I'll see you in the next one.